Hello and welcome to this lecture where we shall be applying the method of averaging to model tubular flow reactors as you have previously encountered in your studies of chemical reaction engineering. So our starting point is in fact the previous lecture where we first introduced the method of averaging, and there we applied it and illustrated the method in the context of the problem of laminar dispersion or Taylor-Harris dispersion in laminar flow tubular pipes. And what we saw there was how in the limit of rapid radial diffusion relative to slower axial convection, we can use the so-called method of averaging to derive a simplified model that made immediately obvious how differential transport due to axial convection appears effectively like a diffusive dispersion in the axial direction. More importantly, we saw how systematically we could derive a so-called reduced order or lower dimensional model where we went from a partial differential equation in the axial direction x and the transverse direction r or the radial direction r to just an ordinary differential equation in the axial direction. And after some manipulation, this ODE could be brought into the form of an axial dispersion model, and we could derive the dispersion coefficient in a systematic manner. Now in that problem, the problem of laminar dispersion, we looked at an unsteady diffusion advection of a solute. In today's problem, we'll focus on a steady state case, but where you also have the solute undergoing a reaction. In other words, we look at trying to model a tubular reactor. Now you have encountered this problem previously, but you have typically looked at it in the ideal case of what's known as a plug flow reactor, where one of the two following limits are assumed to hold. Either you say that there is extremely rapid radial mixing or so-called perfect transverse or radial mixing, which basically means that the axial Peclet number, small p in the previous lecture, which is the ratio of diffusion time in the radial direction or mixing time in the radial direction to convection time in the axial direction. So we assume that this p goes to 0 or is exactly 0. In that case, this plug flow model is valid or accurate. The other possibility is you don't have perfect radial mixing, so p is finite but small. Instead, you have a velocity profile, axial velocity profile, which is a plug or which is flat or non-varying in the radial direction. And this is approximately quite well satisfied in the case of, for example, electroosmotic flow in small tubes, as we had seen in an earlier lecture, where the velocity is driven due to a slip at the wall rather than a pressure gradient. And it's also approximately satisfied in strongly turbulent flow in pipes, which has a flat profile, much flatter than the laminar flow. But if you do have laminar pressure driven flow, which has a parabolic profile, then the only way you get a plug flow behavior is if you have very rapid radial mixing, which in the case of unidirectional flow must be purely diffusive. So it just means that you have extremely small Peclet number. But now suppose as in most real situations, the Peclet number is small but finite, and yet you have a parabolic flow profile, then you can expect deviations in the performance of the reactor from what is predicted due to plug flow. So in that case, how do we obtain a corrected model? Now in your previous courses, you may have encountered models for non-ideal reactors. Either these things are modeled like, for one model is the CSTRs in series. So you say that you divide the kind of plug flow reactor into compartments and model each as a CSTR. Or you can introduce the effect of dispersion phenomenologically. So you just, based on Taylor's analysis of dispersion, you introduce a diffusive term in the axial direction artificially and give it a Taylor dispersion coefficient. Most importantly, this model is what's typically used. Most importantly to note here is that the Taylor dispersion coefficient introduced in such models is assumed to be the same as that in the absence of a reaction. So it's assumed that the presence of a reaction does not modify the dispersion coefficient that has been introduced. Okay, so this is the background of the problem today. What we're going to do now is to take up this problem of transport and steady state transport and reaction in pressure driven flow through a tube, or this tubular reactor problem, we are going to start from the full partial differential equations and then apply the method of averaging which we have already introduced in the last lecture. We shall see how this procedure of averaging, which we are now familiar with, leads us directly to a corrected model that naturally accounts for the effects of axial dispersion along with other corrections arising from the presence of a reaction. More importantly, we'll see that this model can be used to show that an axial dispersion model is relevant, or we can obtain the model in the form of an axial dispersion model. But importantly, we will find that the dispersion coefficient actually depends on the reaction rate and the reaction kinetics. And this is something that was not known earlier before. Even though it was suspected, it was not something that was derived systematically until the use of this averaging methods, again by Professor Vemuri Balakotaya at Houston and his group. And we'll be following one of his papers, which I will refer to in the course of the lecture. So with that introduction, let's begin with the schematic, the problem, and proceed with the averaging procedure. So we begin with a schematic. Let me just change my nib size. Okay, so we're looking at again a cylindrical pipe in which you have pressure driven laminar flow. So this is the velocity profile U star to indicate dimensions, and so we have U star by U characteristic, which is our non-dimensional velocity U, right, having a form that's 1 by 4 times 1 minus r square, which is the same as 2 times the average velocity 1 minus r square. So you can show that the average velocity after integrating this is 1 by 8. So the average velocity here, I should use I'll use a consistent notation with what we use for cross-section average, which is these angular brackets, right, times 1 minus r square, where the definition of this average cross-section average is 0 to r of u dr, divided by r dr. And this you can evaluate, so this is not 0 to r, it's a definite integral, so it's 0 to it's 0 to 1 in dimensional form. So after scaling the radial coordinate with the radius capital R, which I will do in a second, right, I can write this integral as 0 to 1 in non-dimensional form. And this factor is basically 1 by 2, so I get 2 times as a definition of the cross-section average quantity. Okay, so this is the flow field, and again U characteristic here, right, is G r square by mu, where r is the radius. Okay, just a second, we used r as the radius previously, but in this problem we are going to introduce a reaction rate term which we would like to call r. So let me just revise the notation quickly and call the radius of the channel A instead. So when you work out such problems, you might find that it helps sometimes to be careful about the choice of notation, and even if it requires some work, it's sometimes better to go back and change it to a better notation, because that helps and prevents you from making mistakes. So it's useful, I mean, it would, even though capital R seems useful at this moment, let's take the radius of the channel to be A, because that will allow us to introduce a rate of reaction in a more meaningful notation. Okay, so now let me write down my governing equation. So I'm going to look at the transport equation, which has advection, right, axial advection, diffusion as well of the solute, radial diffusion of the reactant or solute, and reaction. So the advection, diffusion, reaction equation is what we're going to start with, under the assumption that we have steady state and that the length of the channel over the radius of the channel is large. So this is the radius, as I said, and this is going to be the length of my reactor. So we have a long, narrow reactor, as is typical in many problems. So if we know already from the previous lecture that under this this limit we can ignore axial diffusion. Ignoring axial molecular diffusion. But as we shall see, the average model ultimately introduces an effective axial diffusion due to the dispersion effect, which is convective in nature. And so relative to that dispersion in the axial direction, this molecular diffusion will be insignificant provided this condition holds. Okay, so then under these assumptions, we can write down the what I would call the full model for our problem, which is the full PDE without any other simplifications. So beginning in dimensional form, we have the molecular diffusivity 1 by r d by dr, where again the asterisk denotes dimensions, a dimensional quantity. So this is the diffusion term minus a rate of reaction, so that I'm going to call capital R to denote my unknown reaction rate term. So the reaction rate, for example, first order would be some rate constant, let's say minus k times the reaction rate C star. But I'm going to leave the order unspecified in our derivation. So I'm just going to call the rate expression capital R, and that capital R is a function, of course, of the concentration. So this term denotes the reaction rate. And this must be balanced under steady state by the convection term. U is, of course, a known function of R, as I've written up here. Sorry, by dou x star, where x is the axial direction. Okay. So this is our governing equation, and then we have the boundary conditions, of course. So we say C star at x star equal to 0. So at the inlet, I have a concentration C in, and I just need one boundary condition here in x, having ignored molecular axial diffusion. And in the r direction, I need two conditions. So I have C star at r equal to 0 for any x is bounded, and I have the no flux boundary condition at the wall r equal to a to be 0. This is the no flux condition. Okay, so this is my full model. The first step, of course, is to scale our problem. So I'm going to do this quickly, since we have already done the scaling of a very similar problem in our previous lecture on laminar dispersion. The only tricky point here is how to scale the reaction rate term when the exact form of the expression is unknown. So I will spend a bit of time on that. Okay, so what I'm going to do is I'm going to introduce a non-dimensionalization of this rate term in the following fashion. I'm going to say that the dimensional rate that I have written here, right, can be written as this rate expression evaluated at the inlet concentration Cn times a non-dimensional R of C, where C is non-dimensional, and the non-dimensional C, right, is going to be given by Cn, or C star over Cn gives me my non-dimensional C, and the expression evaluated at C gives me the non-dimensional form of the rate, and that's of course going to be multiplied by a dimensional term which has the correct units of the rate by using C in as the concentration. So for example, if I have a first order reaction, so if R star is equal to minus, sorry, not minus, I've already put the negative sign out there. So R star is equal to K C star, let's say, where K is of course the first order rate constant. Then I can write this as K times C in C, right, by substituting the scaling of the concentration, and this is nothing but the rate expression evaluated at Cn, which is what I'm calling R star of Cn. So it has dimensions and it's evaluated at Cn, and this C is just R of C, right. Similarly, if R star is equal to second order, right, a second order reaction, then I can write this once again as Kc in square times C square, where again this is R star of Cn and this is just R of C. Okay, so you can see how this can be done for any arbitrary reaction rate kinetics, and you can write it in the following form. So you can non-dimensionalize without knowing the exact order of the reaction, provided of course it's only a function of C. Okay, so we are able to continue with the derivation without at this point having to specify whether the reaction is first or second order or some other order. So now with this non-dimensionalization in mind, keeping that R star of Cn is some constant with the dimensions of reaction rate, which means it's for example moles per unit time, right, or moles per second. Those are units of R star, and R of C is non-dimensional. We can now keep that in mind and proceed with scaling the other terms. So we scale concentration, like I said already, with the inlet concentration. We'll scale the radial direction with the radius, the axial direction with the length of the reactor. And of course we already know that U star is the U characteristic times U, where I define U characteristic in terms of the applied pressure gradient G above. Okay, so under this scaling, we'll find that we can introduce two non-dimensional numbers. So you'll see that essentially I'll get diffusivity over R square here. The concentration scale will cancel out from these two terms, but I will have a concentration scale relevant here. So essentially I'll get D times the concentration scale divided by A square over here. I can divide throughout by that term, right? So I'll get one non-dimensional group here and one non-dimensional group in front of the convection term. Now the non-dimensional group in front of the convection term we have already seen in the problem unsteady advection diffusion problem of laminar dispersion, and that group is going to be simply, right, by looking at here carefully, I'll get U characteristic over L coming out of here, L, and then when I multiply throughout by the diffusive group to retain the diffusive term to be the leading term, I will get A square over D. The concentration scales of course cancel out from the balance of the advection and diffusion term. So the result is I get this product, which is nothing but the diffusive time upon the convection time in the axial direction. This is the diffusive time in the radial direction, and this is what I call the small p, or the axial Peclet number. Okay, and I am of course going to assume that this axial Peclet number is what I am going to take to be small in my subsequent method of averaging. So I know that this is going to be small. That's my basic assumption. So this group appeared in our laminar dispersion problem as well. In fact, there it was the only non-dimensional group. But now we have another non-dimensional group in front of the reaction rate term, which presumably should be a ratio of the reaction time to the diffusion time. So let's look at what that group looks like. Basically, you're going to have R star evaluated at Cn, right, times A square over D and a concentration scale, of course. Right, this just comes from balancing these two terms or taking this group and dividing the equation throughout by that. You'll see immediately now that this is nothing but, again, you have the diffusion time in the numerator and you'll have the reaction time in the denominator. Why? Because remember, R star over C is basically moles per second, for example, and this Cn as moles, so you have 1 over second. So essentially this is 1 over the reaction rate time. So this is the ratio of the time it takes for radial diffusion to the time of the reaction. We've already encountered such a group in the case of reaction diffusion in a catalyst pellet, right, where you could have very fast reaction or very slow reaction and you have different perturbation problems. But here we have this balance also in the presence of convection. So the problem is a little different. Okay, so here we aren't going to consider the case of very rapid reaction per se, so we won't have any boundary layers near the channel wall. Instead, the fastest process is going to be still radial diffusion. So we are going to consider only slow reactions or reactions at most that are as fast as radial diffusion but not faster. Okay, so before stopping here, it would be nice to rewrite this so I can bring in the Peclet number here as well, since this is going to be my perturbing parameter, and you will see things emerge more clearly that way. So to do that, I can write this ratio as Td upon Tc, which brings in the Peclet number, and Tc upon Tr. Right, so this is nothing but the Peclet number times this is of course 1 over R, and the convection time scale is L by UC. And this quantity is called the Darmkohler number, or the ratio of convection time to the reaction time. So the final result is Peclet-Darmkohler is the combination of groups we'll have in front of the reaction rate term. Now remember what I said, that we're still going to say diffusion is the fastest. So we expect this Peclet-Darmkohler to still be small because the Peclet is small. So in other words, we are going to say that Darmkohler is, we're going to consider Darmkohler roughly order 1, right, in our analysis, so that we have the, if we say the Peclet number is order epsilon and we say Peclet is order epsilon. This is our the order of magnitudes on the parameters we are taking. With this assumption, we know that terms involving just multiplied by P are going to be small, like the convection term, but also the reaction term, which is multiplied by P Darmkohler, provided the Darmkohler is itself order 1. So we can't have a problem where the Darmkohler number is extremely large, nor a problem where the Darmkohler number is extremely small, because otherwise the reaction rate term will again become insignificant, and we'll have to change the way we are balancing the problem. Or at the very least, the reaction rate term will come in as a much smaller effect. Okay, so now let me write down the scaled equation. So it's the scaled full model. So I'm using the term full model to mean the model without any approximations or averaging, beyond of course the initial assumptions we made before beginning the problem. Okay, so this has the following form now. We have the Peclet number times non-dimensional velocity, rho by dou x. We then have the radial diffusion term, where R of C is either C for a first order reaction, C square for second order reaction, and so on. Okay, and then remember my scaling, of course, that Peclet is order epsilon. Damkola we're going to assume is order 1. Boundary conditions, of course, we have dou C by dou R is equal to 0 at 1. We know C at 0 is bounded, and C at x equal to 0. This is, of course, R equal to 0. And C at x equal to 0 is 1 after scaling. Okay, so this is now what I'm going to call my equation 1, the full model. Okay, so now we are now in a position to apply the method of averaging by considering the case of small Peclet number, just as we had done for the case of laminar dispersion. So there, instead of the reaction term, we had Peclet dou C by dou T, which was grouped with the convection term. Now we have Peclet Damkola number times the rate of reaction. So the method of averaging is going to proceed very similar in this problem to what we had before, with some small differences. So the application of method averaging is going to be something that's not very new here, but the context and the implications will be different. In fact, it might be a good idea to pause the lecture and spend some time trying to apply the method of averaging yourself to see where you can proceed, and then to come back and watch the lecture. But before we proceed to the method of averaging, it's useful to first consider how this model reduces to the plug flow model of the ideal plug flow model that we have studied previously. So let me first look at the heuristically simplified plug flow model. Right, so when I say heuristically simplified, it means you simplify the model by just using some physical ideas, or even if you scale the problem, you simply set some small parameter to 0 without attempting any systematic estimation of the errors or any systematic derivation of corrected models using perturbation methods or so on. So what we're going to do in the method of averaging has the benefit, of course, of A being systematic and strictly based on a careful analysis of the various orders of the terms, and secondly that it allows us to get corrections to whatever level of accuracy we desire. So we can stop at order epsilon or at order epsilon square and so on, as we do in any perturbation procedure. Whereas a heuristic derivation doesn't give us a way to get corrections, it just gives us the most basic simplified model that can be obtained. So the heuristically simplified plug flow model says a priori, even without scaling, that you have no concentration variation in the radial direction because you have perfect radial mixing. So that is typically the way this idea is introduced. If that's the case, then simply I can ignore, if I have no concentration variations in R, the diffusion term just goes to 0 and I directly get only the convection balanced by the reaction. Another way of seeing this is, even if you don't have no concentration variations in R, the fact that the Peclet number is vanishingly small will also give us the plug flow model. That's not immediately obvious from here, but you can, of course, it's not immediately obvious right at the beginning, but if you scale the problem and you really take the limit of Peclet going to 0, right, you will find that C is independent of R, and then the next order balance is just going to give you these two terms balancing. So yes, sorry, I have to make a slight correction in what I said. This limit is basically equivalent to saying you have perfect radial mixing. Or infinitely fast radial diffusion. You can see this right at the beginning, just heuristically, by saying that perfect radial mixing means C is independent of R, or you can see it from the scaled equations. In either case, you are going to get U dou C by dou X equal to minus Damkola number times the rate of reaction. Right? Now U, of course, cannot be a function of R, so this U is really the average U. So this is where I mean the model is heuristic. So you assume perfect radial mixing, that tells you that the diffusion term has to be 0 because C is independent of R. But then how do you account for U? Now you have removed the radial direction from the problem. So then typically you replace u by its average because, well, what else are you going to do? That seems to be the physically relevant thing to do. So this term is sort of heuristic when you do this kind of hand waving physics based, or physical understanding based argument. But you're not exactly sure whether this term is quite right. Another way of seeing this model is through the method of averaging again, which I will apply now. So when we apply the method of averaging, as you recall from the previous lecture, we're going to average out the original equation, where this average of the u will appear naturally in the convection term. And along the way, we will see how we can obtain the plug flow model either in the limit of p being 0, or more importantly, even if p is non-zero, you still get back the plug flow model if you have a plug velocity profile. So that is not so obvious, or in fact not at all obvious at this point, that if you have a plug velocity profile, even if you don't have perfect radial mixing, that the plug flow model is valid, right? But we will see that only from the procedure of averaging, which is already one benefit of the averaging method, apart from the fact that it gives you a more accurate model by accounting for small but non-zero p. But anyway, let's keep this in mind as being the PFR model, and we'll come back to this at a later stage.